Hi everyone, my name is Emily Wade. I'm here with Ashley Russell and we're the Engineering Chicks. And today we're going to talk about discrete event simulation. So the first thing that we're going to talk about when it comes to discrete event simulations are Poisson processes. And so we'll be introducing a Poisson process through an example. So if you consider the following situation, you're waiting for a taxi on a street corner and you've been told that these pass by in a complete random fashion. So, more precisely, in a small time interval of duration, say h, the chance that a taxi arrives is approximately proportional to h and does not depend on its previous history. So then if you let n of t denote the number of taxis passing during the interarrival from 0 to t, and then suppose that there is a positive constant lambda, which is the arrival rate, such that for any small time interval t of t plus h, then the probability of a single arrival is approximately lambda times h, and the probability of no arrival is approximately 1 minus that, which is 1 minus lambda times h. And these probabilities are assumed to be independent of occurrences in the time period of 0 to t. And so that's an example of a Poisson process. So going from that example, the Poisson processes have the following properties. They have independent increments, which means that the numbers arriving in non-overlapping intervals are independently distributed. And this is the Markov or loss of memory property. And then the second property is that the chance of 2 or more arrivals in a small time interval may be neglected. And then the third property is stationary increments, which means that the distribution of the number of intervals in an interarrival depends only on the duration of the interval. And so one way of simulating a Poisson process in the time period of 0, t is that the first to sample n of t using an efficient Poisson variate generator, and then to sample the arrival times conditional on the Poisson variate. So then for the Poisson process, the probability distribution of n of t can be derived. And so we define p sub n of t equal to this equation, and that's conditioning on the number of arrivals in 0, t, which gives us the following equation right here. And then through calculations and equation manipulation, we can calculate that the interarrival times have this density, which is lambda times e to the negative lambda times t, which might look familiar to you. So then also the mean and standard deviation of the interarrival times are both lambda to the negative 1. So the next thing that we're going to talk about is a time-dependent Poisson process. And this is an important generalization of the Poisson process that we just talked about. And the difference between the Poisson and the time-dependent is that if there's a time dependence, then lambda is replaced by a known non-negative function called lambda sub t. And so that gives us a heterogeneous Poisson process. And so when you replace lambda with lambda sub t, it gives us the following equation. As you can see, there's lambda of t in here instead of just lambda. And then that leads us to a density function that is right here. So that's f of t, where t is less than or equal to 0, or where t is greater than or equal to 0, but less than or equal to t sub naught. So continue talking about our time-dependent Poisson process. Frequently, that analytic inversion of f that I just showed you will not be possible. And so under that circumstance, you're going to want to use an envelope rejection, and that's if lambda of t varies considerably, and a non-uniform envelope will be needed for efficient implementation of that time-dependent Poisson process. And so the general algorithm for that is following right here. For time, I'm not going to read it out, but you can pause the video and check it out even more. So now we're going to talk a little bit about Poisson processes in the plane. And so we're going to consider a two-dimensional domain D, where we're letting C be a subset of D and E being a subset of D, where C and E are equal to rho. and rho is the empty set. So then you're letting n sub c and n of c and n of e denote the number of randomly occurring points in c and e respectively. So then we're going to suppose that there exists a positive constant lambda such that for all c and e and n of c and n of e are independent Poisson random variables with these means right here. And then the point process, which is this statement, is defined to be a two-dimensional Poisson process. And we can think of lambda as being the density of points, that is the expected number of points per unit area. So then we can suppose that D is a circle of radius A, and then we let R1 to R sub n of D denote the rank distances from the center of the circle in the two-dimensional Poisson process. And then that has a rate of lambda. And so then from all of this we can derive that the probability of this density is e to the negative lambda times x. So continuing our discussion of the Poisson process in a plane, we can use the previously discussed algorithm to generate the n of d abscissa for the points. And so using those algorithms, we can come to this following equation that is listed right here, that is g of x over the integration of 0 to x naught of g sub u du. And then we can use envelope rejection with a function that is similar to g of x, and you can suppose the ith such abscissa is x sub I. And that leads you to this equation right here, which is the homogeneity of the two-dimensional process mean.
Alright, so now we're going to talk a little bit about Markov chains. We're going to talk about two types of chains. So we have discrete time and continuous time. And so a Markov chain is discrete valued. So that means that the state space values are finite or countable. It's a stochastic process where the history of the system is irrelevant or unneeded if you know the current state. So to estimate the future, all you need is the current state. Okay, so first we're going to talk about the discrete chains. So a discrete time Markov chain changes in discrete time steps. So the changes in the system happen at discrete times. So a good example of this is a board game like Chutes and Ladders, where the pieces move around on the board according to how the dice roll. So we found a source that summed this up really nicely. So if you're looking at a board at the beginning of someone's turn and wondering what the board will look like at the beginning of the next person's turn, it doesn't matter how the pieces arrived at their current positions, the past history of the system. All that matters is that the pieces are where they currently are, the current system state, and the upcoming die roll, the probabilistic aspect. This is discrete because the changes to the system state can only happen on someone's turn. So this is a really good example of how the past history of the system doesn't really help you understand what the future is going to be like. So all you really need is the current. So next are continuous time Markov chains, and these can change at any time. So a good example would be cars visiting a drive-thru. So a car can arrive at any time, and since arrivals are pretty much independent, if you know the number of cars that have gone through by 10 a.m., what happened before then doesn't really give you any additional information that would be useful in predicting the number of cars that will have visited the drive-thru by noon. So again, this is just showing that the past doesn't really help you predict the future. So for discrete time chains or Markov chains, these changes can only happen at certain times, and with continuous, these changes in the system can happen at any time. So finally, we're going to talk about regenerative analysis. So for this, we need to recall the definition of a renewal reward process. So each inner arrival time is associated with a random variable that is generically thought of as the reward associated with that inner arrival time. So frequently in simulation, we wish to estimate theta, where theta is the long-run reward per unit time, where and when this exists. So we can estimate the long-run occupancy of, for example, beds in a hospital ward, where R equals this equation here, and O of U is the bed occupancy at time U. So over here we have the renewal reward theorem. This is pretty long, so I'm not going to go through it all. You can pause it and look through this if you'd like. But I'm just going to keep going here. So the regenerative method for analyzing simulation output data seeks to exploit the theory that we showed you on the last page by attempting to find renewal or regeneration points. So the advantages of this is that there's not a need to allow for a burn-in period at the beginning of any realization in order to reach a point in the sample record at which it is believed that the behavior is stationary. And also only one realization is required, so that's nice. But some disadvantages are for many systems the cycle length or the time between successive regeneration points is very large. So for example, in a GG1 system, the arrival rate is only if the arrival rate is only slightly less than the service rate, stationarity is assured, but the system returns very infrequently to the empty and idle state. So here's a source that I mentioned earlier. This summed up the Markov chains very nicely. We could have gone more into like the mathematical models behind those, but we thought it would be a little more helpful if we just talked about them generically and gave examples of what they are. But that's all I have for you today. Thanks for watching.